The next attribute that we want to talk about are those horizontal asymptotes for inverse variation. If you recall, in inverse variation, we had horizontal asymptotes because the output of the function could not be zero. When it's a rational function, we can still have horizontal asymptotes, but it's not a true asymptote. It's not that the output cannot equal zero. Because we now have a polynomial in the top of our fraction instead of just a constant, there is a possibility that our output can be zero. In fact, sometimes our asymptote isn't going to be at zero. And so it's not an asymptote in the sense that the graph is never going to touch it or cross it. And in fact, sometimes it will. What we want to think about horizontal asymptotes with rational functions is it's the end behavior of the graph that is being determined by the asymptote. So for example, the one that we looked at yesterday for our vertical asymptotes, if I was looking at this, I would say that my horizontal asymptote looks like it is at zero. It's like right along here. And it is in fact zero. And that looks just like with all the other inverse variations that we did. But if I look at a different example, notice this one's a little different. The ends of the graph, right here, the end of the graph seems to be approaching the number 3. And here, the end of the graph appears to be approaching the number 3. And in fact, the horizontal asymptote is at 3. But you'll notice that the graph actually crosses over 3. So this is why it's not an asymptote in the true sense of the word that the graph can never touch it. That's what we were used to when we did exponentials and inverse variation. And the vertical asymptotes, that's still the case. But the horizontal asymptote isn't really a hard asymptote. It's much more about when you're looking for the horizontal asymptote, it's going to be telling you what's happening at the ends of the graph. What number are the ends of the graph approaching? So it's much more about the end behavior than it is giving us a hard, rigid guideline. It is still very important for drawing the graph, though, because as we draw our branches and what we're looking for, where we're approaching at the end of the graph, it is that guideline for where is the graph going at the far right and the far left. So the horizontal asymptote is still very important to find. You just need to be aware that it's not so much a hard asymptote as it is what's happening at the end of the graph. So how can we tell whether we have an asymptote up here at a number like 3, or whether we have an asymptote down at 0 like we did with our inverse variation? So that's what we're going to look at now. And this is going to require us to think back to what we know about fractions in general. There's a couple of things that I want you to just kind of remember about fractions. There are different types of fractions. If I have something like 2/3, this is what we call a proper fraction. Right? The numerator is smaller than the denominator, and that gives us a proper fraction. Sometimes we can have something like 7/4, and this is what we refer to as an improper fraction, right? So we had proper and improper. And then you have something like 3/3, still fraction. It's not a very exciting fraction. It is technically considered an improper fraction, but I've always just kind of thought of it as a boring fraction because it doesn't stay a fraction, right? It always ends up canceling out and becoming 1. But the idea is that the numerator and the denominator are the same size. And in an improper fraction, the numerator is larger than the denominator. And in a proper fraction, the numerator is smaller than the denominator. And you might think that's a really funny thing about fractions to review, Ms. Parker. What does that have to do with anything? Well, this is what determines what type of horizontal asymptote we have when we're dealing with rational functions. We want to look at the rational expression itself, and we need to determine whether it is a proper fraction, an improper fraction, or a boring fraction, because that's going to determine where and how its horizontal asymptote behaves. Now, when we talk about numbers in a rational function being larger or smaller, one of the things that we want to think about with polynomials is what is it that really makes the number get larger in a polynomial? And that is the exponents. Remember, exponents make numbers grow very large, very quick, depending on the power and what the number is that you're plugging into it. So when we look at rational functions, what we're really looking at is the degree of the polynomial. So every polynomial has a degree. If you remember from the polynomial unit, the highest exponent in the polynomial is its degree, and that determines the degree of that polynomial. So when we look at a rational expression, we want to look at the degree of that expression. So if we look at the problems that we were looking at before, if I look at this first one, the degree of the numerator, it's linear. It's to the first power, right? So it's a linear polynomial. So it's a first degree polynomial. And the denominator is a quadratic. It has a degree of 2. So in this case, the numerator has a smaller degree than the denominator. That makes it a proper fraction. All right? If your rational expression is a proper fraction, that means that its horizontal asymptote is going to be 0. Always. When we have a proper fraction, that means that no matter what number we plug in for x, this one has a higher power. So this bottom number is always going to turn out being bigger than the top number. And as x gets to be a bigger number, it's going to be an even bigger and bigger difference. And so that means that this is always going to be some teeny tiny little fraction that is getting closer and closer to 0. So when you have a proper fraction for your rational expression, the degree on the top is smaller than the degree on the bottom, so you have a proper fraction. That gives you a horizontal asymptote at 0. If we look at the other example, this one we said we had that asymptote at 3, all right? So let's see what was going on with this fraction. If I look, the numerator is a quadratic, so it has a degree of 2. And the bottom was a quadratic, and so it has a degree of 2. If you have a horizontal asymptote that is not at 0, it's at some other number, it's because it turned out to be one of these boring fractions. It's not a proper, it's technically an improper fraction, but they're the same size. The top and the bottom are the same size. So in essence, no matter what we plug in for x, they're both getting squared. That's going to be the same number. They're getting multiplied by this little number. They're not going to be that far off of each other. And then they just have these little constants that as these x's get larger, those make such a tiny, insignificant difference. So really, the only difference between the two is the leading coefficients of the highest power. So when you have a boring fraction, when the degree on the top is the same as the degree on the bottom, so we have those, oh, they're both to the exact same power, they're just going to cancel each other out. That means the ends of the graph are going to start approaching these leading coefficients. So notice the leading coefficient here for the top was 3, and the leading coefficient down here for the bottom was 1. So 3 divided by 1 is equal to 3. And that's why the horizontal asymptote ended up being y equals 3. So when you have a proper fraction, if you have a proper fraction, and that means that the degree on the top is less than the degree on the bottom, that's what makes it a proper fraction, because the top is smaller than the bottom. All right? Anytime that happens, then you're always going to have a horizontal asymptote at 0. If you have the boring fraction, where the degree on the top is equal to the degree on the bottom, then that means that you're going to have a horizontal asymptote at y equals the leading coefficient divided by the leading coefficient. Because those x's are going to be the same numbers, and once they start getting big, they really just end up canceling each other out, and what we're left with is it's getting closer to these leading coefficients. And so that's what is going to be the driving factor for the ends of these. Now, we did not talk about what happens when it's an improper fraction. We're going to save that for tomorrow's lesson, but this is how we find our horizontal asymptotes for rational functions. We want to look at the rational expression, determine whether it's a proper or an improper fraction. If it's a proper fraction, then its horizontal asymptote is always 0. And if it's an improper fraction that's the boring type, where the top and the bottom are the same degree, then we say the leading coefficient divided by the leading coefficient. That is going to be where our horizontal asymptote is. If it does happen to be an improper fraction, where the top is larger than the bottom, then it does not actually have a horizontal asymptote. It has something else, and we will talk about that tomorrow.